Chapter 5.7, Differential Equations. Day 2, Separation of Variables. Yesterday we looked at a differential equation and we verified whether a solution worked or did not. Today we're going to look at how do you find a solution to certain types of differential equations. There's lots of types of differential equations out there. We're just going to look at the ones where you can solve using separation of variables. So let's look at an example. Find the general solution of x squared plus 4 dy dx equals xy. And we're going to use separation of variables. What that means is we want to get the variables away from each other. So we want all the y's together on one side and all the x's together on the other side. Now when you do this, you don't want any differential in a denominator. In other words, right now what we have is we have dx in a denominator. We don't want that. So I'm going to get rid of the dx from the left side by multiplying both sides by dx. Left side cancels, and we have an expression like this. So as you can see from where our dx and our dy are, we want all the x's on the right side of this equation and all the y's on the left. So I'm going to move those around. And as we do that, the y's here will cancel, the x squareds plus 4 here will cancel. We end up with dy over y equals x dx over x squared plus 4. And now with our variables separated, we can integrate. The left side is dy over y, that's the du over u pattern. That's our natural log of y. Again, absolute value of y. The right side, that's x dx over x squared plus 4. That's almost du over u. If u was x squared plus 4, du would have to be 2x dx. So we're close. We need a 2 there. If I do multiply by 2, I have to balance it by also multiplying by 1/2. We now have the du over u pattern. So it'll be 1/2 natural log of x squared plus 4 plus a constant. I put the absolute values in because the natural log you can't use with negative numbers. The left side, it's necessary. The right side, it is not, because when you square a number and add 4, there's no way it can be negative. We'll clean this up a little bit. I'm going to put the 1/2 power inside. So it'll be the natural log. 1/2 power is the square root. And I'm going to finish it off. Get rid of the natural log by exponentiating. We got y equals, and we exponentiate the right side. Whenever you have that plus c in your exponent, we can just do c e to the natural log of x squared plus 4, e to the natural log. Those are opposite operations, which will cancel, and we're left with y equals c square root of x squared plus 4. All right, let's move on, look at another one. This one has an initial condition of 1, 3, and we know the slope. So find the equation of the curve that passes through the point and has the slope given, as shown in figure 5.32. Well, let's take a look. This looks like something that's very similar to a slope field. So we're going to graph y over x squared as a slope field. I got that right there for us. We want to find the equation of the line that goes through the point 1, 3. So right about there, what's that equation going to look like? So let's start by solving the slope. dy dx equals y over x squared. Let's separate, get the y's on the left. So dy over y, the x is on the right, x to the negative 2 dx. Since it's not x to the negative 1, I'm going to bring it up as a power. We'll integrate. So we got the natural log of y equals power up, x to the negative 1, divide by that power, plus a constant. Let's exponentiate. So y equals c e to the negative x negative 1. Negative x to the negative 1. And now use your initial condition. Use the initial condition to find the value of c. So when y is 3, x is negative 1. And negative 1 to the negative 1 is negative 1. Multiply both sides by e. c equals 3e. So when we plug that in, y equals 3e e to the negative x to the negative 1. This is really like e to the 1 there. We've got multiplying exponents the same base, so we can add the power. So we got y equals 3e to the 1 minus 1 over x. All right? And moving on to the last type of problem here. This is the type of problem that is really going to get you if you're not careful. This type of problem has appeared on the last 2 AP exams for sure. Haven't looked back far enough, but it may have been on the last 3. So this is a logistic growth problem. The rate of change of the number of coyotes in a population is directly proportional to 650 minus the number of coyotes in the population. It's a limiting factor. Where t is time in years. When t equals 0, the population is 300. When t equals 2, the population is increased to 500. Those are going to help us find our variables. All right, so let's take our differential, the rate of change of the number of coyotes with respect to time equals 650, or is proportional to, so that means we need a k, 650 minus the number of coyotes. I'm not going to use n of t. You guys know what that is. All right, so let's separate. A little trick here. I don't like this negative n because it's going to make it a little tricky to do. So I'm going to factor that out. Let's make it negative k n minus 650. This makes the problem easier to do. All right, we'll separate. We got dn over n minus 650 equals negative k dt. As we integrate here, all right, dn over n, that follows the ln pattern. That's why we switched it, so that it would follow the ln pattern. So we got the ln of n minus 650 equals negative kt plus a constant. All right, I'm going to continue to solve, so I'll exponentiate. N minus 650 equals ce to the negative kt. And then we'll add 650. The number of coyotes equals 650 plus ce to the negative kt. All right, so let's use that initial condition, or that general solution, to find a particular solution with the initial conditions we got. Right? Our first initial condition is when t equals 0, the population is 300. So we'll stick 300 in for n. 0 in for t. We end up with 650 plus ce to the 0. E to 0 is 1, so it's really 650 plus c. So c is negative 350. So n equals 650 minus 350 e to the negative kt. When t equals 0, the population is 500. That's going to help us find k. So n is 500 equals 650 minus 350 e to the negative 2k. All right, we'll subtract 650. All right, divide by 350, so let's both have our negative 350, so that's really going to be like 15 over 35. We can reduce that further, e to the negative 2k. All right, we'll log that, natural log, 15 over 35, they both got 5s, so that's natural log of 3/7 equals negative 2k, so k equals 1/2 or negative 1/2 the natural log of 3/7. All right? And so that brings our equation from right here, n equals 650 minus 350 e to the negative k. K is negative, so those will cancel. 1/2. Let's move that around so you can actually see what I'm writing. 1/2 natural log of 3/7 times t. And the question is, what is the population when t equals 3? Let's plug 3 in for t. So 650 minus 350, 650 minus 350 e to the 1/2. So I'm actually going to go 3 times 1/2 times the natural log of 3/7. And we will see in 3 years the population of wolves is 551 wolves. Okay? And like I said, that's a lot of work to get through that. And that is why this particular method is so tricky for some people. There's a lot to keep track of. But what you need to do is you need to just keep yourself organized. Do your integration. All right? Get a general solution. If you can get that far, you're probably going to get 1/3 of the points for that problem. Then find your constants, your C and your K. Find your constants. There's going to be 2 in this problem. That's why it's a little different than other problems. And then whatever question they're asking you, you're going to say plug in a value for t or plug in a value for n and solve. All right? So, in summary, how do you solve a differential equation? First, separate your variables. Get all the y's on one side, all the x's on the other. Second, integrate. A lot of times these methods will involve logs. And remember your absolute values. And then when you solve for logs, remember if there's an e to the x plus c, it ends up being c e to the x. It's simplified a lot better that way. And then finally, find your particular solution if you have an initial condition. If you do not have an initial condition, you'll just stick around with your c e to the k or c e to the t.